All right, welcome everyone for the AI for European Wildlife final presentation. This challenge was sponsored by European Wildlife, the SLU, the Swedish University of Agricultural Sciences, WWF, and Huawei. In today's presentation, we have my introduction, followed by the model exploration team. They have a very cool presentation into all the AI models they have tried out for a problem. They are followed by the generalizable pipeline, of which I'll explain the topic in a few seconds. And finally, we'll have some closing words from Magali from the SLU. If you have any questions throughout the presentation, feel free to raise a hand. We'll try to adhere to your questions as soon as possible. So for the people who are new with us today, we are Fruit Punch AI, and we are the global AI for good community. This means that we believe that to solve humanity's greatest challenges, we need to educate AI engineers at scale with an ethical and sustainable mindset. So how do we do this? We do this by creating AI for good challenges. An AI for good challenge is an AI challenge that is gearing towards one of the sustainable development goals. So we're doing challenges in wildlife protection, conservationism, but also in clean energy transition. We've done, pretty much in all SDGs, we've done some challenges now. In these challenges, we tackle a data problem in 10 weeks with a team of 25 to 50 AI engineers that come from all over the world, from all skill levels. So it's a really good opportunity for new AI engineers to gain some skills, but at the same time for experienced and machine learning engineers to apply their skills for a good cause. For today, we are going to tackle a problem of generalizability. So in the AI for Wildlife challenge, we are basically tackling one problem, which is that for conservation, we use camera trap data. They are mounting very large numbers of data sets from all over the world. These camera traps are located in forests, everywhere. So you can imagine that they record so much data that at some point it becomes very difficult for a human being to analyze it all and to basically do any species monitoring on them. To automate this, there has been a lot of tries to do some object detection on animals or classification, but we keep running into one of this, basically the same problem. That is, if a data set is very location specific, then models trained on this data set will not generalize well to other data sets. In this challenge, we have tried to tackle this problem by creating a generalizable pipeline which takes in data from large open source projects like Trapper or Agouti, and then trains a model on it, evaluates it, and deploys it on new data. As part of the challenge, we also tried out to work with the mega detector. We tried to go from detection to classification. And apart from playing with the mega detector or YOLO v5 model, we also explored some new models. So that's a bit what the context of the challenge is about. Over the last 10 weeks, we worked on this challenge. We ended up with two groups, generalizable pipeline and model exploration, and we ended with 26 engineers who have put in over 2,000 hours of engineering. Our goal was to build computer vision models to accurately detect and classify wildlife and trap images, and also to be able to deploy those models. The challenge started on the 25th of April, and today you are present at the final presentation. The team will have one more week to finalize the report, and then you will be able to also read back all the results in more detail. You can check out our platform, FruitPunch.ai, app.fruitpunch.ai, where the results will be posted. But for today, I won't take up too much of the time because most of the interesting presentations will come from the team members. So I'd like to invite Team 1 to start their presentation.
All right. So I'm Agneta. I'm the coordinator for the model exploration team. And I'm just going to introduce the team quickly, talk about our goal Then we'll move on to solutions and results and a demo. And then we'll look at some lessons that we've learned throughout the project. So our team has been really multidisciplinary. We've been looking at state-of-the-art model training, but we're computer and machine learning engineers, data scientists, ecologists, physicists, and people from all sorts of different levels. This is some of us, and you'll hear from Alba and Ricardo and Akash later, but it's been a big team of lots of very nice people to work with. So our main goal has been to find a state-of-the-art computer vision model that can expand on the current capabilities of Megadetector. So Megadetector can already detect humans, animals, and vehicles, but we want to classify more species to improve the object detection metrics, and also to generalize to diverse environmental conditions, like Dorian said, different seasons, different times of the day, and different regions.
Yep, thank you. So, well, as Dorian said in the introduction, it's very important to monitor fauna because this gives data of species occurrences in the wild, providing information for estimating relative abundances, population dynamics, or mapping predicted distributions as seen in this map of European Environmental Agency. Next one, please. So in the model exploration team, we had the following specific objectives, which are fundamentally to train a state-of-the-art model with a meaningful subset of the initial data and fine-tune this model for a reliable inference. Next one, please.
So, hi, I'm Alba, and I'm just going to give you a brief introduction of the data that we have for the challenge before we go into all the models that we try and we choose. So first of all, the data belongs to two data owners, which are the Rewilding Europe and SLU, which stands for the Swedish University of Agricultural Science. And for this challenge, they provide us with a chunk of data from two different platforms that they use to host their data. So for Rewilding Europe, they use the data, or their images are coming from a platform called Wildlife Insights, and for SLU, the data is stored in a platform called Trapper. And also, to give you some numbers, from the Rewilding Europe, we have access to one data set that had more than 500,000 images. And from SLU, we had access to two data sets, and they were both around 40,000 images in total. So next slide, please. So now I'm going to talk about one of the biggest struggles or the biggest problems that we find when we are starting the challenge, which is the unbalanced data. And this means that the number of images that we have for each species was different. And as you can see here in this graph, for some species like the reindeer, we had almost 3,000 images, but for most of our species, we had less or around 1,000 images. So we had clearly an equal distribution of classes, and that can be a problem because it can cause potential biases towards certain species when you are training your model. And that can result in a negative impact in the performance of your model. So we tried to tackle this problem, and we end up having a script that goes through several steps to try to have a more balanced data sets for training any model. So if you go to the next slide, please. So our script goes through several steps to get to this balanced data set. And so the first thing was we used all the data coming from both Rewilding Europe and Trapper, and we merged them into a unified data set, and we removed all the nulls. And nulls were those images that were not associated to any species, so we didn't use those ones. And after putting together all the data set, we had to reindex or create new classes IDs so that all the species had the same ID. Because imagine, for example, one of the Trapper data set, the domestic cat was ID 1, and in another one was ID 5. So we had to make sure that using the common name as a reference, that all the same classes had the same ID. So after that, of course, we had to update the ID associated to each bounding box, so they were associated to this new ID that we just created. And finally, to create the final data set, we used the deployment ID and the common name as the main fields, because we wanted to make sure that we had a fair distribution of classes across all the deployments. And finally, we put a threshold of 1,000 images per class. So for those species that we had more than 1,000, we choose a subset, a random subset, and for the ones that we have less, we just use all the images. And finally, we divide the data into training, validation, and testing. Next slide.
Well, so first of all, we reviewed some existing deep learning models, but considered two types mainly, those in the YOLO family and one vision transformer, as you can see in this slide. Next one, please. So to select these models, to choose one, we use the following criteria. Most important are that they have to be open source available in public repositories, so we can replicate trainings with our datasets. And of course, we looked for a high ratio of optimal results and time efficiency. In addition, while training, we followed the criteria of balancing the data, as Alba explained, and reporting the same metrics to compare models. Next one, please. YOLO V5 has been the main state-of-the-art model for object detection and classification, and of course, it's the base model of mega detector. Moreover, YOLO V8 has been developed by company Ultralytics and stored in a GitHub public repository. It improves the precision of V5 models and also includes several improvements based on earlier versions of YOLO, like YOLO X, V6, 7, or PP-YOLO-E. It is also highly efficient and can be run from CPUs to GPUs, and also have a large community of developers for maintenance. This is very important. Next one, please. So YOLO-NAS, on the other hand, has been developed by DC AI company with also has a public repository. It has been reported to outperform YOLO V8 with high accuracy and latency. Its version of size L reaches same accuracy of other YOLO models more efficiently. Next one, please.
Slightly different from those is the multi-scale vision transformer, MVIT V2. It was developed by Facebook AI Research Affair and UC Berkeley, and it's available in the Detectron 2 repository and also on Hugging Face. As state-of-the-art performance in classification and in object detection. And for this project, we were thinking we could either use it as a backbone for a two-stage object detector with an RCNN, or it can be used as a classifier. So for example, using mega detector to detect animals, crop the animal out, and then using MVIT V2 to classify the animals after. The results we got from this, because we started working on it a bit later, are not directly comparable to the other ones. So we won't report those here, but I understand that it has been sort of tentatively incorporated in the pipeline. So you might hear about it in the next presentation.
So, however, a preliminary comparison between the YOLO models show a good performance by YOLO V8. This model was chosen as the best model to fine-tune in the next steps. Possible failure in precision by YOLO-NAS might have been caused by an inadequate hyperparameter tuning, as the documentation is not well explained for this moment, model at the moment. Next one, please. Well, as we can see here, these images detected by YOLO-NAS, there are some image misclassifications, including more than two objects in the same image, or misclassifications. So now our colleague Akash is going to present the YOLO V8 results.
Hi, thanks. This is Akash. I was the product owner of this task, along with Ricardo out here. Because we analyzed the different types of SOTA models, I was working on the YOLO V8 model, and we tried to experiment it across 36 different experiments. For that, we took a smaller sample of the data set, because training it across the entire data set would take a lot of time. So we took a sample of it and then trained it on different parameters that we have. The best parameter for MMAP 50 was around 0.85. There is, as you can see, there's a 10 to 15% kind of a jump with the hyperparameter tuning that we see out here. So just to read this, the last part of where you see the bar is where you see the metrics for the model. From left to right, you see the different learning parameters which has been adjusted. Okay. Please go to the next tab. Yeah, so these are some exploratory plots which show out the kind of the distribution with the different classes. As you can see, that the classes is slightly there is a long tail to that, but however the height and width, that is the x and y coordinates of that image, is pretty much normally distributed across. So can you go to the next slide? So, and this is a confusion matrix from the best the 36 experiments that we performed. These are the F1 curve, confidence curve, and the confusion matrix. As we can see that the more the data, the better the accuracy is there, but it still gets a good amount of classification across the entire set. And there is some level of normalization that needs to be done with respect to the label set as well as this, but that would give us better accuracy. Next slide, is it a demo? Okay. So this is the precision, the PR curves that you see out there. The dark blue line is the best line of the best curve. That is the average map across all classes. The other lines that you see is the individual PRs for each of the classes. The map 50 for the 95 percentile was around 0.761. That means that the 95 if it is 95% confidence, that is a 0.76. Well, map 50, which is the average map average precision values, is around 0.84. And you see the loss, the box loss values, the classification, and the DFL loss. The box classification loss is say if you have the ground truth of the bounding box, what is the accuracy with which the model is able to predict on top of it, which is around 0.747. And classification loss is the loss which it gets in classifying the individual objects. DFL is basically the flow loss, which is utilized for. This is one of the parameters that you can tweak to get a better performance with respect to the object detection and classification. I will share my screen. What we did was we deployed a model on Hugging Face, and I will showcase that, and we'll see some samples run on top of it. So maybe this is the screen. So this is the Hugging Face spaces that we have, and you can upload it, submit it, and you will see the output out here. So I'll show you an example out here. Say this is from the validation set that I'm taking. So there's no fitting on that. So I'll submit this. And this, mind you, this is running on a free instance. So it has 2 virtual CPUs on which it is running and 2 GB of RAM. And as you can see that this is an interesting photograph. I'm not sure if you can see it from your end. You will see 2 deers who are sitting at the back, and there's one in the front. But I think this was a good output, as the box is, if you see, it's captured the one in the foreground as well as 2 deers who are sitting in the back, right? Show another example out here. So these are sheets, domestic sheets. This one shows the processing time, and it's mapped it. So 1, 2, 3, 4, and 5 sheets that you map. I'll try to take something which is in the dark, which is like a file pool. And if you can see, it's below out here is file pool. So that so it typically seems to be working well. There are some places where it's still there's a requirement for normalization, which could help us. For example, I'll show you an example of. Let's try to take this. What happens over here? And these are dark. I think they are some type of a deer, maybe a roe deer or a fallow deer. And okay, it gets fallow deer is what we're getting. But if you see at the bottom out here, it's probably got a red squirrel out here, which is false positive. Yeah, I don't know if there is something that I don't look at it closely, but typically it works. That's all from this.
So in terms of lessons that we've learned, I think some of them were very expected, like generalizing to different environmental conditions can be difficult. Real data is unbalanced, and that is sometimes also quite difficult. Small animals can be really difficult to detect. And when we tried to work around this, we found that some of the solutions that are out there are really computationally very intensive. And selecting appropriate confidence thresholds for testing and inference can also be really difficult. We had some limitations in terms of computational resources, different levels of expertise in the team, different sort of time zones in terms of finding time to meet, also the fact that we also have other jobs. But still, in terms of future directions, we'd love to be able to get our best models to generalize to new species, which I guess is sort of what the pipeline team have been working on. We'd want to try to improve image augmentation, for example, by using virtual data generation to get around the unbalanced data problem. We want to work on optimal thresholds to be adapted to the goals specified. Maybe to explore the hyperparameters of YOLANAs to see if we can get better precision, and then look at maybe other edge machine learning frameworks. But all in all, it's been really fun. And I don't know if we're taking questions now or if we're taking questions later.
Thanks for the presentation, Team 1. Good job. Yeah, let's do some questions right now. Thanks for the pretty demo, Akash. So since it's on Hugging Face, is it possible for everyone to just access it now already?
Yeah, I have not made it public, but I'll make it public. I'll post the link on the Slack channel so you can use it.
Nice.
The model is also posted on Hugging Face as a model. So let's try that.
All right.
I have a question to Akash as well. So I was wondering, you said that you trained on a subset of of the images for Yellow V8. So how many images did you use and how much time does it take?
Yeah, so I might show you the. You want me? I'll show you the distribution of it. Okay, so it's so what happens is that when you train it with large images, it takes a lot of time. So the current model which is deployed was trained around 24,000 images. Okay, training, and another 3,000 for the validation part. Now that takes around 7 to 8 hours to train. Right. Now, if I want to do hyperparameter tuning with this big size, I'll have to take 8 hours into 32 experiments, which would be a big, entire month would go off from that. So what I did was take a sample of it, which was around 200 images per class. Okay, so that would be 200 into 30. That's around 6,000 images. 6,000 image was what we looked at, and 6,000 images. Each epoch takes me 1 hour to do. Each training of 80 epochs takes 1 hour. So we could have 32 hours, and 32 hours you have 32 experiments out there. And taking the best parameters, we then trained with the larger size, with more data. That's it.
Great. Yeah, great. Thanks.
Awesome. Thank you.
So, well, hello everyone from me as well. My name is Adrian. I will be presenting the progress for the generalizable pipeline team. and well, I suppose it will be a similar structure to what the first team presented. So I will briefly introduce the team, then well, I will not actually spend that much time on the problem since it was very nicely introduced by the model exploration team already. But yeah, of course, then on the goals and the results of our team or sub-team in particular, and where we struggled and what solutions we found. And again, or similarly, we'll also wrap up with some lessons learned and next steps to do. Well, our team also was decently sized. Had a bunch of nice people to work with, also across time zones and continents. And well, we've also faced similar struggles with respect to availability and so on. But in the end, the people that stuck around to the end of the challenge were involved and pulled their weight. So yeah, like I said, the problem was nicely introduced already. So just a few brief words as to what it meant for our team or our sub team. And I suppose the most relevant point for that is that there was well, first of all, the amount of data is decently large, so there are many camera trap images to go through when researchers compile their studies, and many of those are empty sometimes. And there existed a solution already consisting of mega detector to run say a first filtering classification to at least detect when images contain a human or animal or they're blank. But there were also some, and there are also some limitations to mega detector, and most importantly that it only has a few generic classes, and with animal species it's pretty inaccurate. Though it does, like I already mentioned, it does help in saving time by sifting through images and filtering out the irrelevant ones. So the goal for our sub team was to develop a pipeline that could take a model and use it end to end from fetching data from Trapper, training a model, comparing different models on the same data set, and then generating some, or also performing validation and then generating some predictions, some observations, and pushing those back to a Trapper project. And the one of the key points while doing this was to make it possible to develop a multi-class, an accurate multi-class detector, so that species information could be enriched using such models. And well, then this pipeline could be used to train models and specialize models by retraining them on different location-specific data sets from different deployments and locations. So this is what we end up with. I think I will actually zoom on it a bit. Nah, that doesn't seem to work too well. But well, we have essentially two main components in our pipeline. So the two containers here in the middle, one of them on the right side, which we call minimum viable product. So essentially what we can deliver at this moment is a Docker container that contains a bunch of models. So the YOLO family, YOLO v5 and YOLO v8, but also as well like the someone in the previous team mentioned, also a vision transformer. And those models can be run, well, because with the magic of Docker, we can ship them on new systems. Then those models can be run pretty quickly from the command line using a bunch of command line convenience methods or utilities that we developed, and I'll actually show them in the end in the demo. But yeah, those models can be used to train on data from Trapper. They they can be validated on the same on data from Trapper, and then inference results can be generated. And in the same container, there are a few convenience methods, again, the command line that can be used to actually download data from one or more projects from Trapper and to push observations back into a Trapper instance when inference has been run with a model that researchers selected. And in parallel to this, we also have an MLflow web user interface that is deployed, that can be deployed next to this Docker container, also in a Docker environment, just to for portability. And if done so, if this MLflow instance is also deployed in parallel to the MVP, then a bunch of metrics are actually logged during all steps of the pipeline. So when downloading data, when running training, when running inference and validation and so on. And there also during training, some metrics are logged and the runs are logged in a weight and biases instance that I'll actually use to show some runs. But that's a bit out of the scope of our pipeline in particular. And in the context of the MVP, you actually see the steps that I mentioned. So if you look on the left-hand side, that's the training or retraining path where we can download data, convert annotations. So the bounding boxes especially, they need to be converted from the format that Trapper uses to the format that models use. And in this case, because we were focusing at least in the beginning on the YOLO family, then we needed to convert to the YOLO format. That data can then be split into subsets, and we can run training on that data set. And of course, we need to save the weights of a train run, so that's also there. And then on the other side, the inference pipeline. So when we have a model that we decided we want to use for generating predictions, then if we need to download data again, then we can do so. And then, of course, we can run inference and the resulting predictions, which is essentially a table full of species and bounding boxes information. Those can be pushed back into a Trapper instance. And, well, as mentioned, MLflow tracking is actually the lines should be a bit extended here because more of the steps are logged than just inference and training and download. And you see, well, these HTTP connectors, because that's the protocol that we communicate with, that we use to communicate with Trapper. So, well, speaking of struggle, so, well, I've already discussed a bit the solution direction for this. So we have essentially two pipelines, one for training and retraining, and the other one for inference, and both are Dockerized. They can also be run natively, of course. It's the code can be run natively, granted that requirements are met by the system, but they can also be run in this way with relying on Docker. And, well, also the MLflow instance that I described earlier over that diagram that receives logs from the pipeline using HTTP calls essentially. Oh yeah, and well, we've also had Akash in our team, and he was busy downloading and preparing the rewilding data set. So that was a large amount of images actually. And in terms of data augmentation, our pipeline contains a wrapper around the implementations package, so that can be used for augmenting data and generating a bit more. And it's pretty configurable. And now, yeah, I jumped the gun a bit, but now on struggles. So, well, we noticed that implementing certain augmentations on some on certain images was it was a bit challenging because those well, they had certain characteristics that made them more difficult than others in the data set, and that was usually related to segmentation and pose detection. And we've also a bit late in the process discovered a bug in, well, either Trapper or the way we were interacting with the API that caused bounding boxes to be well, downloaded wrong when we used a larger when we try to download more images at once. So that's something that we still need to investigate. And we tried setting up a local Trapper instance ourselves so that we had something to test with, and so that we didn't to test with and not break someone else's project. But that proved to be a bit challenging, at least in the time frame that we had available. So now we actually have, with help from Magali, we have a playground project on the Sweden instance of Trapper that we can use to do more testing of the pipeline. And the testing that still needs to be done is to make sure that the format is correct for outputs, and that they can be actually injected back into Trapper correctly. That's the part that still needs to be confirmed. And well, yeah, I also promised a short demo. So well, our pipeline consists of essentially a Python package, and like I mentioned, there are a bunch of command line interface utility methods. So methods that can help users download data from Trapper, run inference, run validation, train models, and also to upload observations back into Trapper. And well, the rest of the code is probably not extremely interesting for this presentation and can be looked at after. But there's also a README that comes with it that explains how to use each of those convenience methods, and how to actually do some tasks with them. So to download a few to download some data from Trapper, and well, do a bit of validation. So maybe already try the mega detector weights and see how well that works with the existing data. Yeah, generate some results with that. Train a new a Yellow V5 model, initially perhaps for the task of classifying between animal and human, but also somewhere later to use well, more classes, so to actually get into the realm of species enrichment. And the nice thing about the way the code is set up is that well, using a machine from FootPunch and the functionality from GitLab CI, we were actually able to set up a CI, between quotes, I suppose, pipeline that could be manually triggered to start doing training. And you can see, well, this is just one run I selected where the training was basically triggered from the GitLab CI using the Docker environment. So the Docker container that I mentioned in the the slides. And this is actually, you can see here one of the convenience methods that we implemented. So this one was for validation this time. And runs are actually logged on weights and biases. And for example, there's a run where we used the model detector, mega detector weights to just detect between human, animal, and blank. And you can see a few predictions from that run here as well. And similarly, because I also showed in that README that you could also do training on more classes, then you also see a train with, I believe this was a yellow v5 model. And you can also see, for example, well, a few predictions of some cute rabbits and dogs and whatnot. So, well, back to what we actually learned from this. Well, now the pipeline is essentially standalone, so it can interact with Trapper, but Trapper is not necessarily aware of the existence of this pipeline. So that would be a very useful next step. So working closely with the Trapper team and seeing if and how we could integrate this into Trapper itself, so that it could be triggered from the Trapper UI and it could be used from the same platform without a user having to worry about using Docker and whatnot, or installing packages and so on. So yeah, well, that was actually something that we envisioned early on, and like I showed in the diagram, the MVP is what it is now, also because of time, of course. However, if the pipeline is to be run standalone, that's entirely possible. Though right now, let's say low-hanging fruit for improvement would be to actually come up with a few predefined use cases, because at the moment a user would need to actually chain, let's say, the commands together and use our convenience methods in the some would say logical order, but also to configure those and run each one individually at the command line, and having a few use cases like fetch a bunch of images that are not classified from this project on Trapper, run classification immediately after with just the small number of classes, so similar to what Mega Detector does, and then upload those results back to Trapper, all automatic without requiring much user intervention. That would probably be very useful. And similarly to fetch those images that are classified simply between animal, human, and blank, and then do the species classification on those and upload those results back to Trapper. So a few of these use cases would be nice to be implemented in the pipeline. Well, the last point is perhaps irrelevant if the first one is implemented, but we wanted to mention it as an alternative. So if direct integration within the Trapper code base proves to be either out of scope or difficult, then serving the pipeline that we built and the models that are packaged in it as a web service would still make it much easier to use than users having to use the command line and so on. Yeah, well, that's actually the presentation we had from the pipeline team. So thank you very much. And well, if any questions, then.
Thank you very much for the presentation. Very nice. I mean, it's a lot of work that you guys have been able to put in over the last 10 weeks. I'm really impressed, actually. So yeah, good job, guys.
I have a question, but I can concur with Dorian. I'm also really impressed with how much of this you got together, because we knew from the start that it was kind of a stretch to get everything together, and it seems like you've managed to do it within this short time. So really impressed as well. I have like two small questions on the process, how you got there. So you basically had to abstract from different types of models, right? That you're able to run. So the standalone mega detector, but also the trained YOLO v5 and the transformer-based one. Like, how did you go about that abstraction? Like, how did you do that in code or in architecture?
Well, actually, that was a bit of a late step, and it's also a bit of a work in progress in especially for no, I think I'm wrong because I was looking at the code base earlier, and that is also implemented. We essentially have wrappers around the training scripts of each model that is integrated. But it was a late step in the sense that for a long time we were just using the scripts that came with, for example, the YOLO v5 repository or the Ultralytics package, so that you could use for training YOLO v8 and so on. But now in the code you have, am I still sharing? I am. You have essentially a few wrappers around the models that are integrated, and those are actually what get called from the utility method that you get to the command line, and then depending on the model, we do the conversion.
Very nice. So in this way, it would also be relatively easy to add more different architecture.
Yeah, indeed. It does require a bit of coding, of course, because then that conversion needs to be done in code. But yeah, it is definitely possible. And then, well, also the ML flow logging you see here.
Looks very nice. Then one more question. So you build this abstraction in wrappers, and it also seems like both the training and the inference pipeline, including also the ML flow Docker, are all very relatively abstract. The thing that feels kind of fixed for me is the part where you integrate directly with Trapper to fetch data. But let's say that would, I guess, be relatively easy to replace with a line that points to a directory, for example. How deployable would this be on any other type of object detection problem?
Well, now that you mention it, maybe the fact that this is not completely automated through all steps is more of a silver lining than a it's a feature, not a bug. Because the downloading and the training are well, pretty much decoupled. So indeed, the downloading is, and I think also inference, if I'm not mistaken, and probably validation because you need ground truth. I think those are pretty coupled with Trapper because they also download the observations from a particular project and then they use those for validation, for example. But training, yeah, just chooses a model and looks at the data that you pass to it. Maybe there is a bit of tweaking that we could still do to make it completely decoupled from Trapper, but as far as I'm aware, it wouldn't be much anyway. So deploying it to another object detection problem is fairly straightforward. But again, you would have to somehow get that data in that proper Docker volume yourself without relying on the methods we expose here.
No, but still very cool that it's that abstract. The also reason that I'm asking, of course, there are many object detection problems that people are solving, not only with footprints, but also specifically in this branch of detecting wildlife, we've also come across many other platforms similar to Trapper, or at least that have overlap with Trapper. So it would, of course, be very cool if maybe in time I'm dreaming here to like deploy this to multiple of those solutions and be able to help a lot more biologists that are also leaning on some of these other platforms. So cool for thanks for making this huge leap in that direction.
All right. I think that's it for the presentations then. Thank you, Adrian. You can stop sharing. Yeah, so really good. I want to give Magali some final words and then I'll round off the presentation.
Yes, Yeah, so I can actually only say a really big thank you from the whole SLU team to all of you. And yeah, we appreciate a lot that you put so much effort and engagement and all your free time into this challenge. I saw you working in the evenings and the weekends. So really big thank you from us. It was really nice also to see yeah, how you shared your knowledge and your skills to bring this challenge to a really great end. I mean, these results are really amazing. And yeah, I was a bit involved in the model exploration team in the beginning, and I have to say that I was really impressed also how we work together. So in such a respectful way, and you are from different nationalities and backgrounds and all over the world, and still you managed to, yeah, to pull this off together and be a great team. So it was really nice to see that as well. Yeah, I mean, I'm not sure, I don't have to say too much about the results. I mean, the conclusions are really amazing. It's really useful for us. I think not only what you like the output it's on its own, like the pipeline and but also the whole research that you did around it, about the different models, if they are useful, if they can be useful or not, and why not, and all the lessons that you learned and that you summarized so nicely here. This is super useful for us, for also for the future and for future development of these models and the whole AI community, I guess. So yeah, thank you very much for your involvement and in this challenge, and I hope that you enjoyed this challenge as much as I did.
All right, thank you, Magali. I'm sure. I did enjoy it at least as much as you did. I hope all the participants did so as well. Yeah, thanks everyone for joining the final presentation for the team members. Next week is the deadline for the report and the code collection. Everyone, oh, there's one last question.
No, sorry, just the wrong button.
Okay, that's fine. Yeah, next week we deliver up all the code, so make sure that it's nice and structured on GitLab. If you want to put in some extra time to help Magali out with basically finishing the last tasks of the project, you're always free to do so. You can contact me or Magali or anyone else to keep going on with the challenge if you like. That's also why we do all these projects open source, of course. But yeah, thanks everyone. That leaves me only to thank you all for the last 10 weeks. It has been a pleasure to meet some of you and to work again with a lot of you. I'm very happy to have met all of you, and I hope that I will see you in future challenges as well. Yeah, for today, I want to wish everyone a very fruitful evening, or fruitful day at least. And I hope to see you all very soon again.